What's up, everyone? It's pre-calc time with yours truly, Miss Wesley, and really I should be saying it's calculus time yet again as we continue to talk about the derivative, that instantaneous rate of change, and how we're going to find it. I'm at the top of my derivatives packet, page 5. You're going to want to locate probably that so you can take some notes, try some problems, as well as, since it says finding derivatives on the calculator, grab your calculator for a future question because we will be using it in some problems to come. As you're finding those things, I will dazzle you with a joke. Have you heard of the king who is 12 inches tall? They say he was an excellent ruler. So this first problem will just be a review. So far we have the first definition of derivative that I just scribbled down up here that says, let me move myself out of the way, it says that you can take a limit as x gets closer and closer and closer to the value c of the slope of what we call a secant line. And that limit will end up giving us the exact slope of the tangent line at a certain point at x equals c. So we should be able to review and use that to do number 1. It says use the first definition to find the derivative of this function, this parabola, at a certain point at x equals 1. So we're using 1 for c, right? So we've seen this a little bit already. F prime of 1, derivative of 1 at 1 is what we care about. And we're going to take the limit as x approaches 1 of what? So of f of x minus f of c. So we'll go f of x, x squared plus 1, minus f of this value. So minus f of 1. I'm going to plug a 1 in where I see x squared. So it'll be a 1 squared plus 1. All over x minus c, so we'll say 1 on the bottom as well. And simplifying this, let's see what we get for this limit. So you've got x squared plus 1, but then minus 2. Let's call that x squared minus 1 over x minus 1. Glancing at the value that we would hope to plug in with direct substitution, I believe we could just factor the top and get the bottom to cancel. So we'll say limit as x approaches 1 of this difference of squares factored, and that should get rid of our problem in the denominator. X minus 1 is reduced to 1. And you can do direct substitution. So according to the first definition of derivative, plugging in a 1 for x, we've got 1 plus 1 equals 2. Nice to get an answer. Good to remind ourselves of what that answer represents. That means in a second, we're actually going to graph this function. We're going to use it for an example a little bit down the page. So might as well just get that out of the way. It's a parabola shifted up 1 unit. And what we just found was the slope of the tangent line at x equals 1. If I constructed a tangent line here, which I probably don't need for this particular picture, I might just get rid of it in a second, that tangent line would have a slope of 2, which was the answer we got for this first example. So then going back up, it says, okay, could we do this on the calculator? Could we check our answer? Because lots of times there is stuff that we do by hand where the graphing calculator has a quicker way to do it. So you may have seen this, we may have looked at this a little bit before, but your calculator has a derivative function in it, and it's under the math menu. So I'm going to give this a try, and we'll see one of two different types of notation depending on which type of calculator you have. So I'm on an 84 plus CE, and we will do, I'm going to hit the math key to find that derivative function, and it's option number 8, and deriv. My calculator shows this notation, this interface here, and I'll show you exactly what to type in. Just in case you're working on an older calculator, I'll give you that notation as well. So your calculator, if you've got this notation, your calculator is waiting for a variable of differentiation. You're taking d for derivative with respect to what variable? I ended up just typing in x in that first slot, and I'll write that down too. What are we taking the derivative of? Well, we're taking the derivative of the function x squared plus 1. So that's not that much to type in, so I'll type it in x squared and then plus 1. Now, the calculator is really good at taking the derivative at a certain point, like what we just did. Where do we want the slope of the tangent line? We want it at x equals 1. So that would be the very last thing to plug in this notation. Hit enter, we check our answer, yay, we got it right as a 2. Just in case you're working with the other notation, and if you want to record how we would get that on the calculator, you never know when it could come in handy, You've got a d dx in general if we're differentiating with respect to x. We always plug in the function here, either by typing it out, or you'll see later, or using the y1 function. We might use that further down the page. And then you've got, if your variable is x, it wants to know, well, where do you want the derivative? At x equals, I'll just put a number sign here, at a certain x value. I'll put maybe c value, right? We usually say we want the derivative at x equals c. If this pops up, like if you didn't get that notation on your calculator, you still use these same three things. You type them in a different order. If your calculator gives you n deriv, it'll always be n deriv of the function that you want. So you'll type in first your f of x, the function, right? I'll type in x squared plus 1. You use the comma key if you're working on an older calculator, and the comma is right up here next to the parentheses. You see a comma there? We'll do the variable of integration, which is going to be an x, and the last is your c value. I'll put a number here, and that's going to be your c value where you want the derivative. Okay, so cool that we could check and answer. But for what we're going to do next, let's use the calculator the whole way, because it says we can get this value another way. I already typed in, I'm going to go to y equals, and why don't you type this in with me? Maybe clear out any equations you already have in there, turn off all your stat plots, and I typed in x squared plus 1. And we can see it graphed on a zoom 6, a standard negative 10 to 10. Well, you also could find the derivative value at any specific x value right on this graph on your calculator. So it says you go to the graph, you're going to hit second and the trace key, which we've hit a lot along the years. There are things we've used in previous math courses. You could find any value, given x, it'll give you back the y. You could find zeros of a function, mins, maxes, intersects. Do you see anything more useful? Number 6. dy dx is a certain notation for derivative, right? It's the derivative or the change in y with respect to x. For future reference down the road, 7 will be very handy when we need something called the antiderivative, the integral. But for now, let's choose the derivative. The very next x value you type, watch what happens. I'm going to type in x equals 1, enter. And then bam, not only, my calculator is so nice, it not only gives me the x and the y value at that point, look above it, it gives you the derivative value there. So we've confirmed a few times now, or a couple times now, that the slope of the tangent line at that point is going to be 2. Okay, so keeping this in mind, check out number 2 here. It says to graph what we've already graphed and graph its derivative. That's something we haven't done before, is actually to graph the derivative of a function. So let me go back to the calculator. I'm going to go down to y2. This is kind of a cool thing to try. And I'm going to type in that same derivative notation that we just used to check our last answer. So I'll hit math. Oh, actually, so make sure your cursor is down at y2, right, first. Make sure you've got the equation typed into y1. And while I'm on y2, I'll hit math number 8 and deriv, right? I get that same notation here, but I'm going to set up my y2 so that it will always graph the derivative of whatever equation I have typed into y1. So it's still derivative with respect to x, a d dx. You're still typing in, you could type in x squared plus 1, but why don't we set it up so it gives us whatever we have typed into y1? I'm going to use the variables key for this. So I'm going to hit vars for variables right next to the clear key. I go to y variables. I'll hit enter for function because I want a function. And which function do I want? I want what I've typed into y1. So this is a nice setup. So it will graph you the derivative of whatever is in y1. Last question, x equals blank. So usually we put an x value here, right? When we wanted the derivative at x equals 1, we typed a 1. We don't want the derivative at one certain spot. We want the calculator to graph the entire derivative function for every x value. So you know what? We're typing it for x equals all x. If you go x equals x there, this should be a good setup to graph the entire derivative. I'm curious to see what this thing looks like, and I probably should have taken some guesses first, but let's see if we can graph this, hit graph, and then just make our own observations. So my calculator is pretty nice, not to brag, but it shows me the derivative in a different color. I can see it in red, and I want to make some observations. I notice that the original was quadratic and the derivative went down a degree, and that is no coincidence. That will always happen, that the derivative will be 1 degree lower. It's going to be linear. Another thing I noticed, let me sketch this right on the graph. So I'll put this on the graph, just a rough sketch of it. I'll change to red too. And I notice that, where the derivative kind of goes right through the origin. I kind of missed the mark here. So it goes through the origin. Where the derivative is positive over here, where the red graph is above the x-axis, do you notice the blue graph is always rising? And that should make a lot of sense, right? Where your rate of change, your slopes of tangent lines are positive and getting increasingly more positive, this derivative graph is all above the x-axis. Derivative is 0, right? Right where you'd have a horizontal tangent line, right where the slope of the tangent line would be 0. This will be a big thing we come back to. And look, the derivative is negative. It's below the x-axis wherever this original graph is falling. So I'll put some negative signs here. Interesting. I want to do a little bit more. This says, now can you graph another very similar looking function, y equals x squared plus 5, and its derivative? What do you notice? So, if I go back to the calculator, I'll type in, I'll just overwrite y1, and I'll put a 5 here. Think of what should change and what shouldn't change about that original graph. So it should be the same exact shape, but it should also be shifted up 4 units higher than the other one. When I hit graph, okay, predictable. I got the same exact shape of the original function, but just shifted up. And then look, the big thing here is the derivative graph did not change. So one thing that's cool is, and I'll sketch this on the picture, even if you have this same shape shifted up higher, this could be your other function, the next function, it's shifted up to a y-intercept of 5, it doesn't change the shape of the derivative. The derivative is still negative when it falls, and it's positive afterwards when it's rising. A vertical shift, kind of a cool observation, has no bearing on the slope of the tangent line. A vertical shift is just going to keep, the slopes the same thing as it was before. I want to do one more of these. So it says, 3 says, can you graph, a cubic function and its derivative? So let me go back to the calculator. I'll clear out just y1, and then I'll carefully type in this cubic function. So x to the third, what's next? Minus 5x squared minus 8x plus 70. This ever happen to you? You get stuck up in the exponent spot. So let's take 2. Minus 8x, and then plus 70. This one shifted way higher. I can tell already, I don't want to change y2. I still want this to graph the derivative of what I typed into y1, but I want to zoom this way out, especially make my y max higher. You don't have to do much to your x's in this window. I hit the window key. I'm just going to go -5 up to 10. I'll just do a little less room on the negative side. For the y's, can you go like a -20 all the way up above 70? Let's go up to 80 or 90. Change those two things. I'm going to hit graph. I should see a cubic function, just enough room to see it rise and fall. And then I want to sketch the derivative right by it. But notice some things about this function, its derivative. Seems like the original, right, was a cubic. We could have predicted that. Rises, then falls, then rises. And if you go back to your calculator, you'll see something else happens that's predictable. It's a parabola, right? It goes 1 power lower, the derivative. Also, look at this peak in this valley. At exactly the spots where the original function f of x hits a high point and a low point, notice on your calculator that f prime, the derivative, is going to be 0 there. So this, I want to draw this very purposefully. So this is a parabola that has zeros at the exact spots where the original function f of x hits a turning point. Same stuff too about the positives and negatives. Where the derivative is above the x-axis, that's a portion where the green graph is rising. Ooh, then the green graph starts falling. Notice at that point, derivative dips below the x-axis. That's no coincidence. And then bam, turning point, we have a 0 of the derivative, and then we're going to see this original graph rising. So those are my main observations. I'm going to actually pause and write them out for you here, and then we'll talk about them. So hang on 1 second. I'm back, and I wrote down these observations, and I'd recommend pausing the video so you might be able to jot them down too. But all stuff we figured out about the graphs of derivatives and things that could help you out anytime you're trying to graph a derivative. Okay, stay tuned for some more twists and turns. Talk to you soon.